Hello, this presentation is about polar form of complex numbers, or putting complex numbers into polar form. By the end of this presentation, you should be able to identify the polar form of a complex number, graph a complex number using modulus and argument, convert from Cartesian form to polar form, and convert from polar form back to Cartesian form, multiply and divide in polar form. Okay, what do we mean by the polar form of a complex number? Well, here's our Argand plane. I'll just draw a little Argand plane. Remember, we've got our real part of z here, which is the x component, and our imaginary y component. And here's some complex number. I'm going to call this z, and you remember z equals x plus yi, where x is the real component and y is the imaginary component of z. Now that's Cartesian form. That's how we deal with things in Cartesian. In polar form, we're interested in the radial distance from the origin, and we're interested in the angle from the positive direction of the x-axis. So we would talk about that instead of z equals x plus yi, we're going to talk about the radial distance and the angle. Now those of you with a keen eye for mathematics would notice there's a little right angle triangle, and we can use good old sine, cos and tan. If you look here, you will notice that this distance here, which is the y value, is the same as the sine of that angle. So we would say y equals r sine theta, and the x distance equals r cos theta. So we're going to use this property, and we're going to say if x equals r cos theta and y equals r sine theta, then I can convert z equals x plus yi becomes z equals r cos theta plus r sine theta. And what does that tell me? I can take the r out as a common factor. R outside of cos theta plus I times, it should be an I there as well, by the way, sine theta. Now in mathematics, we like to make abbreviations. We abbreviate that to r cis theta. The cis stands for cos plus I sine theta. So r cis theta stands for r cos theta plus I sine theta. Now, how do we work out what the r and the I and the y are? Let's go to our next slide. We'll just draw this. Again, here's our point. There's our angle. Here's r. This distance is y. This distance along here is x. And that's a right angle triangle. Using Pythagoras, we can say, well, r is the square root of x squared plus y squared. That's Pythagoras. And so we use Pythagoras. The important thing about this, r has to be greater than or equal to 0. We don't like to have r as a negative number. That would mean it's going backwards. We call r, this is called the modulus of z, or sometimes we just say mod of z. So that's important to us. To work out that angle theta, theta is the inverse tan of y over x. As you can see from the thing, opposite over adjacent, tan theta equals y over x. Now theta is called the argument of z, or sometimes we go with arg z for theta. So we say that, we abbreviate that to arg z. Now what you would notice, theta can have many values because this angle, our positive x-axis, can go in lots of different, go around the circle lots and lots of times. So we would restrict the argument to what we call the principal range. We restrict arg z to the principal range. And the principal range that we're going to use is minus pi to plus pi. So we're going to use that, and some people use capital arg. Some people, when they have the restricted range, they use a capital A to say I'm in the restricted range. I'm not going to do that in my videos. I'm just assuming that we're always going to be in the restricted range. Okay, here's an example. Let's call this example number 1. I want to express 1 minus root 3i in polar form. Well, a good idea is to draw where is 1 minus root 3i on the argand plane. So here's our real component, our imaginary component. The real component is 1. The imaginary component is minus root 3. So it's going to be down here. So there's z. You can see already, just by our knowledge of triangles, if that distance there is root 3 and this distance is 1, that's one of our known triangles. I can almost guess what the answer is going to be here. But let's have a look. R equals square root of x squared plus y squared. So we'll find the modulus. The x is 1 and root 3 squared. Well, that gives me square root of 1 plus 3, square root of 4, r equals 2. And think about that. That's one of our known triangles. 1, 2, root 3. And from that, you can probably guess what the angle is going to be. Because tan of theta, theta is the angle in here. Theta is the angle from the positive direction of the x-axis. Tan of theta is opposite over adjacent, which is root 3 on 1. So tan of theta is root 3 on 1. So theta in this case is pi on 3, which, because it's going in the negative direction, is negative pi on 3. How would we write that? We would say, well, 1 minus root 3i in Cartesian form is the same as 2 cos plus I sine theta of minus root pi on 3. I'll just put that in a bracket so that we know that that's cos plus I sine of that. So this is Cartesian, or sometimes called rectangular form, and this is polar form rectangular form because it's x and y, polar form because we're looking at the radial distance, the modulus, and the argument. Okay, let's do another one. You might like to do this one first before I do it. Let's go again. Here's my first thing I'm going to do is draw this with my real part of z and my imaginary part of z. I'm going with x equals -1 and y equals -1. There's my z down here. Now when you get the hang of this, you'll be able to do this almost directly from the diagram. So I'm going to say, well, there's my triangle that has 1, 1. We know that triangle is going to have square root of 2 as its hypotenuse, because that's Pythagoras. We also know that that angle in there is going to be 45 degrees. 45 degrees in radians is pi on 4. Having said that, we're not interested in that angle in there. We're interested in the angle from the positive direction of the x-axis. So if that's pi on 4, then this is minus 3 pi on 4. So we can do it from the diagram. Let's check that using our rule. R equals square root of x squared plus y squared. So R equals square root of 1 squared plus 1 squared gives me square root of 2. And theta equals inverse tan of 1 on 1. Inverse tan of 1. The first quadrant solution is theta equals 45 degrees or pi on 4. Remember, this is in the third quadrant, and we have our all sine tan cos. Third quadrant, tan is also positive. So tan can be positive in the first quadrant or in the third quadrant. So -1 minus I is this in Cartesian form is the same as root 2 cis pi, pardon me, undo that one, minus 3 pi on 4. Why minus 3 pi on 4? That's our first quadrant, but we're in the third quadrant. So theta equals minus 3 pi on 4. This is our first quadrant solution. This is our third quadrant solution. Okay. We're up to number 3 now. You might like to have a go at this before I start. This time I'm going to convert from polar back to Cartesian. And this is actually easier than it seems, because I'm just going to expand that 3 root 2 outside of cos pi on 4 plus I sine pi on 4. And you would know 3 root 2 cos of pi on 4, well, that's 45 degrees, is 1 on root 2. And sine of 45 degrees is also 1 on root 2. What does that give me? That gives me 3 root 2 on root 2 plus pardon me, my mistake, 3 root 2i on root 2. Root 2's cancel out. I'm left with 3 plus 3i. So that 3 root 2 cis pi on 4 is in polar form, is the same as 3 plus 3i in Cartesian form. Okay. Where do we use this? Well, we're going to look at multiplication. And I'm going with some definitions here. Here's my rule. Z1 equals R1 cis theta 1, and Z2 equals R2 cis theta 2. Then Z1 times Z2, I multiply the two moduluses together, R1 times R2, and I add the two arguments together, cis theta 1 plus theta 2. So multiply the two moduluses, add the two arguments. Okay, let's do an example. Let's find the product of, I want Z1 equals 20 cis 20 degrees. I'll do this in degrees. We don't use degrees that often in polar form, but you can. And Z2 is 30 cis 40 degrees. Help if I copied my example down correctly, but you know, we'll get it out. Then Z1 times Z2 is 20 times 30. That becomes my modulus. And cis 20 plus 40. 20 degrees plus 40 degrees. Well, 2 3s are 6, so that would be 600 cis 60 degrees. And you might say, we might want to convert that into Cartesian. Well, how would we convert that into Cartesian form? We'd say, well, 600 cos 60 degrees plus I sine 60 degrees, which becomes 600. Cos of 60 is a half, plus I sine of 60 is root 3 on 2. Let's write it as root 3 on 2i. Take the half out the front. That becomes 300 plus 300 root 3i. Okay, and that's multiplication. Now we want to look at division in polar form. Same deal again. I'm going to start with my Z1 as R1 cis theta 1, and Z2 is R2 cis theta 2, and I'm going to say, well, Z1 divided by Z2, well, I'm going to divide the moduluses, and I'm going to subtract theta 1 minus theta 2. So I'm going to subtract the arguments. Let's look at that let's do an example using this rule. So again, I'm going to operate in degrees, even though it's just as easy to do this, and in fact more common to do this in radians. So Z1 is 15 cis 75. Z2 is 5 cis 15 degrees, and I'm going to say I want to find Z1 divided by Z2. Well, what do? The 15 divided by 5, the two moduluses, cis 75 take 15 degrees, which gives me 3 cis 60 degrees. Again, I could convert that into Cartesian form. 3 times cos 60 degrees plus I sine 60 degrees. And that gives me 3 times a half plus root 3 on 2I, which gives me, I could leave it like that, or I could go with 3 on 2 outside of 1 plus root 3I. Okay. By the end of this criteria, we've talked about identifying the polar form of a complex number, graphing a complex number. I haven't really done much of that, but we'll go into that in more detail. We know about the modulus and the argument, converting from Cartesian form to polar form, converting from polar form to Cartesian, and multiplying and dividing in polar form. And that's the end of our presentation.